Welcome to this webinar. My name is Mattia Obreza. I'm head of Gene Bank Information Systems at the Global Crop Diversity Trust. So thanks again for joining us for our for the webinar on accession subsets and trait datasets in Genesys. So quick outline, a very brief introduction to Genesys for those who may not be familiar with it. We'll look at collection subsets, including some background information, and then the practical things in Genesys directly. We'll do a Q&A. Then we'll look at trade data and how that is done in Genesys. Some time will be spent on the background information to explain things, especially the descriptors and descriptor lists, which are crucial to understanding trade data, and then the data sets themselves and how that is handled by Genesys, obviously, with Q&A after that. So for those who don't know, Genesys is an online platform where gene banks publish information about accessions maintained in their collections. And I invite you to have a look at the recording of our How to Use Genesys webinar that is accessible online. So if you missed that webinar, please have a look at it. It does explain the basics of Genesys, how to navigate it, how it works. But today we're focusing on subsets and trait data sets, so I'll skip most of the bits about passport data. Right, so first we'll look at collection subsets, what they are, what purpose they serve, where they come from, and then how to navigate and find them in Genesys, and how Genesys presents the subsets to users. Right, so at its core, subsets are basically lists of accessions. That's more or less it. There's no magic here, but there's a lot of magic in how they were created, why they were created, and there's a bazillion different methods of creating a subset of accessions. So if subsets are just lists of accessions that for whatever reason form a useful set of material for users, then it's really critical to explain to the user what the list is all about. So the metadata, the description about the subset, is actually key to making sense of it and key to understanding the purpose of the subset. Without the metadata, without the description, a title, it's just a list of accessions that makes very little sense to anybody, right? So if you select some accessions on Genesys, you put them in my list, you've created that list for your own purpose. You know exactly why you put those accessions in a list. So that is a subset that makes sense to you. But anybody else who would look at that list of accessions, that wouldn't just make no sense to them, except that it's a list of accessions. So the metadata that describes the subset is key, right? And Genesys does require a title and a detailed description of the subset, and also allows the gene bank to categorize or link the subset to a specific crop. The title and description really are there to explain what this list of accessions is and why it exists, right? Another part of the metadata is the list of creators of the subset. So basically who made the subset, and this deals mostly with attribution to the authors who spent maybe months or years in preparing the data that then eventually allowed them to generate the subset in the end. It's important to note also when the subset was created. The age of the subset, or at least when it was made, gives context to the user, because things change. The composition of accessions in a collection will change as new accessions come into the collection. So what a core collection was 10 years ago may actually not be a core collection representative of the, let's say, maize collection today in a specific gene bank, just because new material has entered the collection. So the dates are important when describing the subsets. And the method that was used to generate or to create the list of accessions is also critical. It explains how this subset was created and gives the user some idea of the effort and the rationale of why the accessions are currently in a list. Right. We have two different types of subsets in Genesis. Uh, you're mostly familiar with core collections, which is one of the most common subsets that you'll find. And that is a representative subset that is basically a selection that still represents the entire collection, but is just strategically selected to be, let's say, 10% or 10% of the 10% for mini course. Another representative subset is, for example, a set of standard trait check varieties. So in specific trials, when researchers look at, for example, drought tolerance, they want to have exactly the same varieties or the same accessions in their trials that will show whether that show the highly resistant and highly susceptible things to, for example, to drought, so that they can make sense of the rest of the material in the trial. Selective subsets, on the other hand, are things that are focused on a specific trait. For example, a list of accessions with high tolerance to drought is an example of a selective subset. And we also have a number of different subsets that look at the types of use. So if, for example, you look at the maize collection in CIMMYT, you could easily make a subset of accessions that are popcorn accessions and say these are the things that are popcorny, and you can find them in our gene bank. And any other curated list of accessions, for example, accessions that have digital sequence data in an external repository, could be grouped into a subset and say these 3,000 accessions are documented and their sequence data is accessible on that external system. Or a list of material most requested from your gene bank in 2019 is a curated list that you create once. It's limited in scope, but it gives users an idea of what that list means and actually might encourage them to select material from that list. So subsets, in a way, are a mechanism for gene banks to promote a part of their collection to users for whatever reason, right? So it's really up to the gene bank to come up with useful, meaningful, purposeful lists of accessions to facilitate or to inform the potential users about the options that they have. And the really neat thing about subsets is that they are just lists of accessions. So they don't need to be backed by data directly. So Genesys does not require the data that went into the analysis, but it's really just the results of the analysis that get published as a subset in Genesys. And that allows gene banks to come up with various creative ways to slice and dice the collection and make it more interesting to different types of users. So we've covered some basics on subsets, and let's have a quick look at how Genesys presents a subset to its users. So I'm going to jump here. So this is one subset as found in Genesys. In this case, this is the chickpea core collection, and as mentioned earlier, it does come with a description of the subset. It includes some classification that this is a chickpea subset. It explains that it has some 1,900 accessions in this list. It was published by ICRISAT, and the subset itself was made in 2001. This subset also provides a link where you can find more information about the subset itself. And this could link to the publication that the researchers prepared, because some subsets are really extensive in the sense of, or the methodology to create a subset can be really extensive and can take a lot of resources to come up with the final list. Following the key information there, you'll find the attribution, so the list of persons involved in creating the subset. You will have a few links supported by Genesys to filter the accessions and browse and see those accessions in the subset in a map. and the primary part of the subset, which is the list of accessions directly, right? So in this case, we would expect to find 1956 accessions. So it's a pretty long list. And what this, at least what Genesys allows you to do is actually say, fine, add all of these to my list directly. My list is something we explained in the previous webinar, but perhaps more interestingly, you can filter out those accessions. So from the 1900 some accessions in the subset, you could still look at how they are classified into different types. You'd say, okay, I'm only interested in the traditional cultivars, and I'm only interested in things from Mexico, for example. And from there, look at the accession list and download data from Genesys. Download the passport data of accessions in this list from the system. So I'll just remove some of these filters I've applied to get back to the subset. Let me see if some of them are historical. No. So putting them on a map is a similar thing provided by Genesys. So these the accessions rendered here on this map are the ones in the subset we looked at. It gives you an idea of the geographical distribution of accessions in the list. And from here, users can make a bit more informed decisions about what material they would select for their breeding program or other research purposes. Right, so there are a few different ways to get to subsets in Genesys, right? So one of the methods is when you're on Genesys entry page, there's an explore subsets link here. If you hit that, it's going to bring you to the browser of subsets registered in Genesys. And this may be a bit overwhelming, so I'm going to focus just on the chickpea subsets here. The filtering behaves the same way as all the filtering across Genesys, so you should be familiar with that as well. If you want to do a full text search, you could say, fine, give me the core collections only. And if we remove chickpeas, we would get quick access to subsets across in Genesys based on the metadata search through this filtering mechanism. So let's go back to the chickpeas. Right, so there are many different types of subsets you will find in Genesys. For example, just there are 4 subsets in for chickpeas in Genesys today. 2 of those are core collections, and 2 of them are lists of accessions. In this case, resistant to Fusarium wilt, and in the next subset is a set of accessions tolerant to heat stress. So subsets are really convenient, just sorry to repeat, but they're really a convenient mechanism for a gene bank to say, this stuff is very useful. You should really have a look at these few accessions because it's a simple way to promote a selection that you made based on your experience when working with material directly. And as I said, it may not require publishing the rest of the data in case you don't want to publish those data sets. And we'll talk about data sets in a little bit. So we had chickpea core collection open before. So the mini core collection is similarly described as the one earlier. It has a much smaller number of accessions in this list. So if the other one was about, well, close to 2,000, this one's 10% of that, or around 10% of that. And the really important part is that the reasoning why this subset was created, and this is usually described in the subset description directly. Further, when it comes to lists of accessions that have a desirable trait, again, it's really helpful to users that the subset is documented and it explains the limitations of that list, and most importantly, when that list was created. and by who. So this is roughly the details on subsets. You can access subsets through the Explore menu under Core Collections and Other Subsets, which will bring you back to the same system. Or if you are really adventurous, you can search for subsets containing, which will directly apply the full text search on the metadata about those accessions and list the matching subsets. In this case, we do get some subsets from other gene banks, in this case, from ITC, CIMIT, and so on, just dealing with the same fusarium resistance or susceptibility. Let's have a look at trade data and what that means and how Genesys can support gene banks and users in accessing the trade data. Okay, right. So trade data in gene banks, right? Trade data, as we just discussed actually, is the one that is of most interest to researchers because it does allow them to do their own analysis. They can do whatever modeling they want. They can mix it with all sorts of other types of data and in making the selections they want. So it's part of their proper research, looking at the available trait observations, linking it up with other things, maybe genomic data, linking it up with climate data, linking it with soil data, and then from that coming to some conclusions and eventually putting those, selecting the material that they want to further develop or select for further development or use, right? And most of the time when we work with gene banks, data usually is found in Excel files, CSV files, in rare cases in databases, and in all cases this comes with some sort of limitations. But it is crucial to make this data available to researchers to help them find the material of interest. Right, so when we're talking about data about plant material, and I'm skipping the passport data here really, we are dealing with passport data, phenotypic data, morphological, genomic, molecular, marker data, sequence data, performance data, you name it. So there's a number of different types of data that gene banks deal with. Some of it accessible to users, some of it used internally. And as I said, one of the data types is the passport data. We won't look into that today, but it's basically where the material comes from, or where it originates from, and what species or crop it is at the very least. The more interesting, however, is the characterization data. So this tells us more about what the material looks like, what the seed looks like, what the fruit looks like. And these characterizing traits are generally highly heritable, and characterization data is most useful to both gene banks and to users. To users in making their selections, and to gene banks, it allows gene banks to quickly check, or basically to check that the material is still true to type. So if something's supposed to be yellow, and when you grow it out and it's blue, then you are immediately alerted that something probably went wrong and there was a potential mislabeling of samples, and it's something that you need to look into. And this data is of high value to researchers, as we mentioned as well. So this characterization is normally done by gene banks, whereas evaluation stuff will be typically carried out outside the gene banks. That is, evaluation is usually done in different environments, and the results generally depend on treatments applied. So this is much more researchy than the pure characterization of material. And with evaluation, it's really important to document and record the conditions in which the evaluation was done, and what the purpose of those things, what the purpose of the trial itself was. We have standards in recording this type of data, MIAPI, so minimum information about phenotypic plant, something, is something that helps you document in a lot of detail the trials and the conditions and treatments of each trial. Right. Yep. Right. So regardless of the purpose of the data itself, the absolutely most important thing is to document how trade observations are made and how they are recorded, right? So this is generally recorded in descriptor lists, and I'm pretty sure you're familiar with descriptor lists published by IBRI, FAO, Bioversity, and you may have even participated in developing some of these lists. So these published lists aim to provide standards for recording of traits that should make the data understandable and compatible between research programs and across institutions. Published descriptor lists can be easily found on the internet by searching for crop name descriptor lists or in Genesys. But the problem here is that researchers and institutions tend to not only pick and choose the traits of interest, they also may adjust how the trait is observed and actually then how it is recorded, just out of convenience or because the descriptor as defined in the list is perhaps outdated. Things are evolving and changing. So even if you say we are using the published descriptor list for chickpea, there is a high chance you have descriptors or that you are observing traits that may not be documented in that publication, or that you have developed some additional descriptors that you want to record. In any case, this results in highly customized descriptor lists and a huge variety of how data for the same trait is recorded over time and between different institutes, well, and obviously across different crops. So let's look at some of the definitions to make this discussion a bit easier, right? So descriptors define the trait, how the trait is observed and how it's recorded, and we need that information to be able to exchange data, to store it properly, to use it properly. And each descriptor consists of a name, the descriptor method that explains how the trait is observed, and possible descriptor states, which is basically how the trait values are recorded. And these definitions are sourced from Bioversity's guidelines for the development of crop descriptor lists. So I will try to make these links available to you later on. Now, the best thing to do right now is to show you an example of a descriptor list in Genesys before we go further. So I have picked one here. This is a descriptor list from Africa rice. It includes a title of the descriptor list and the description or the rationale where this list of descriptors come from. These are rice descriptors maintained by Africa rice, and the version of this descriptor is 1.0. Now, what you'll find here is then obviously the descriptors, the individual descriptors that form this descriptor list. And I'll use this opportunity just to navigate through here and give you an idea of what descriptors will look like in Genesys and what descriptors, descriptor definitions here mean, right? So the descriptor obviously has its title, which is usually something in the form of object property. In this case, we're talking about the number of days until 80% of plants are heading. This is a characterization descriptor, and the data type in this case is numerical. When you have descriptors that measure length, the unit of measurement is usually provided, and it's recorded separately for each descriptor, and so on and so on. When we're dealing with a list of options that are encoded, these are then provided with labels, and optional description for each of those labels. In this case, the descriptions are not provided. And I just want to find one more representation of a descriptor definition in Genesys that's a bit different from the other ones, just to give you an idea. Hold on. And I do believe it. I'll find it somewhere down here. Right, so here we go. In this case, there's one type of descriptor definition in Genesys that comes with this type of representation. But basically, it says the data observations are made on a scale from a min value to max value, and labels are provided, or a legend is provided on some of those options, though 4, 6, and 8 are also valid observations for this descriptor. I think with that, I will return to the presentation. Right, so going back to the definitions in the publication of the guidelines for development of crop descriptor lists, there's a few possibilities about how descriptor states are recorded, and you can see those on this side. So we'll begin with qualitative characteristics, and these are either nominal, ordinal, or binary according to that publication. And nominal is basically a list without any sensible order or ranking. It's a list of options, in this case, yellow, orange, red, brown, purple, which would be encoded as with values 1, 2, 3, 4, 5, or A, B, C, D, E, or something similar. There is no sense of order in this nominal scale. In ordinal scales, these are lists that are ranked in a numerically meaningful way. And this is the one that is most commonly used for, I'll explain a bit later, but it is very commonly used to say, when you're looking at a trait and you say, okay, it goes from low to high, from short to long, from not susceptible to highly susceptible. You have binary descriptors, which are basically yes, no. Common examples, absence and presence of something. And then on the other side, we have the quantitative characteristics, which are either recorded as continuous values, so real numbers. They are the exact measurement of a trait, or maybe an average or a mean value of the measurements of a trait. And this can assume, an infinite number of real values. So basically, it's not a limited set of options. So this is usually what you'll have, where you'll find also the unit of measurement, like meters, centimeters, percentages, counts, and so on. And there's also this discrete section here, and this is a very commonly used way for gene banks to share their data. And it is basically a ordinal scale, like in this case here, where actually the values, or the ranges of values, are grouped into discrete classes and then are represented as an ordinal scale. Now, this is not really used when precision is required, because once you have converted proper observations, proper traits, trait observations from their numeric exact measurements into discrete classes, there's no way of going back. And it's also subject to how people make these observations, how they classify it. So if your option is to say this is short or long, instead of saying it is 50 centimeter, it really depends on who's doing those observations. Right, so I'm trying to find the mouse again. Right, so going back, the exact measurements are most useful for statistical analysis, and the researchers really would prefer to have those types available to them when they are downloading and using the data sets provided by gene banks. Right, okay, I need to rush through this. Right, so when registering descriptor definitions in Genesys, you obviously specify the descriptor title and describe how the trait is observed. And the gene bank may pick from one of the following data types, to document how the data is actually recorded in the data set itself. So free text is commonly found in various data sets that we see. It's basically just a free-for-all, a text that maybe describes the state of a trait, or is perhaps just a comment. We usually see dates, for example, exact flowering dates, exact, I don't know, excuse me, even harvest dates, looking at duration of between the harvest, planting and harvest, and things like that. We see a lot of binary data, so Boolean yes, no type of data. And then we have obviously characteristics that come in a data set that are recorded as numbers. So that's the numeric type, which are real numbers or integers. They usually come with a unit of measurement. And we do advise gene banks to also include let's say a valid or expected value range for such traits. So basically to say, okay, we expect the values to be between 0 and something sensible. If nothing else, the value range for numeric traits allows you to spot if something is perhaps way out of hack, and it sort of indicates a data quality or data transcription issue. Then a very common thing you'll see is coded descriptors or coded traits, where each of the possible values, so nominal, scale, comes with a label, and we've seen some of those in the Genesys descriptor list earlier. And finally, we have a data type that, unfortunately enough, we call it a scale. So think of it as in, how bored are you right now on a scale from 0 to 10, and the range must be specified. So from 0 to 10, and preferably a legend would be provided that says, 0 stands for I'm not bored at all, 3 is a little bored, 5 is somewhat bored, 7 is very bored, and 10 would obviously be the one that says I wish I left 30 minutes ago. So this type of scale is also rendered differently when you're looking at the descriptor definitions in Genesys. Okay, so let's look at data sets in Genesys. Right, so let's do it this way. Okay, so Genesys allows gene banks, actually, if gene banks want to publish data sets or trade data sets in Genesys, Genesys forces them to publish well-documented data sets. What that means is that each data set, so remember that Excel file we saw a few slides ago, if that is the data set that contains very valuable data that took a long time to generate, that file exists. The next important step is to describe to the outside world what that file actually means. So with that, the dataset title and description are key and must be provided, and must explain enough about the conditions and the environment and the objectives of the data sets, and how things were done. This is followed by contributor attribution, which you'll see here. So in Genesys, so we understand it takes a lot of resources and a lot of time to put together a data set. So attribution of data set creators is critical, and we do try to highlight the people involved in generating the data set. So in this case, we have two people that contributed. We have data sets that go into, let's say tens of contributors. It is very important to have information about the licensing, so the permissions to reuse the data set. Without the information about how the data set can be reused, you are getting into, well, it becomes tricky to start if somebody would want to take the data set and make use of the data you provided. So most commonly, some level of attribution is required by gene banks that publish data sets in Genesys. Now, obviously, the main part, or actually the interesting part to researchers, is the dataset file itself. uh, which is in Genesis exactly as you keep it or as you prepare it for publication. Most commonly, these are Excel files. We do see some CSV files every now and then, but it's highly likely that your trade data exists in a shape of a single file and not a database. If it's in a database, generating a file from that is also simple. Now, we discussed this a bit earlier. The locations, so in this case there was one location, but the evaluation may have happened in multiple locations at different times. This is something that needs to be recorded or can be or should be recorded with each data set that is added to Genesys. And this information informs the user of, let's say, the geographies, the climatic conditions, in addition to whatever treatments you may have also described in your publication. So the next thing in the description of a data set in Genesys is obviously the list of descriptors that you have, the list of traits you have observed, and the ones that you expect that the user can expect to find in the data set. The traits observed obviously are the descriptor definitions we have just discussed. So to publish any data set on in Genesys, first thing that you need to do is document your traits before then attaching the data sets that are using those descriptor definitions, because that only that way the user can start to make sense of the values they see in the Excel or in the dataset file. And finally, one of the last bits of the metadata about the data set is also the list of accessions that are described in the data set. Now, this is most useful because you don't want to be adding passport data to all your data sets. You only need to link the accessions that belong to the data set to that record. And with that, the user will be able to directly, download the passport data only of the accessions in this data set and then put the two together. So trait observation and trait data sets come to Genesys from one side, but then as passport data curation happens, next year or later, passport data will change and you don't want to be re-uploading the trait data sets all the time. So with that, if we take passport data out of the data sets and just properly link them up through DOIs or through accession numbers, then anytime the person downloads a data set, they also will always have, through Genesys, access to hopefully current and accurate passport data about the accessions described in the data set. Right, so with that, I think I can show you what that looks like. So again, I've picked a data set in Genesys. This is a characterization data set of tomato from World Veg. It describes it gives a bit of background what this contains. And these were accessions characterized in 2013 and 2016, following descriptor lists used by the World Vegetable Center gene bank, right? This contains 37 accessions and those were evaluated, or the data set hopefully contains data on 58 different traits. Now, why I say hopefully is because the data can be sparse. So even if you have, it's not a completely filled grid of traits and, sample, you will have some gaps in there. So the coverage is something that we consider before publishing a data set. So if you say, I'm describing 15 traits, but then we only find values for one, we'll get back to you and try to clean up the data set before publication. Actually, this is the exact data set we were looking at in the presentation. So we have the attribution, we have licensing information. We can download the file as provided by the gene bank. Upon download, you will get the terms and conditions, a prompt about respecting the terms and conditions of use. You can download passport data. Okay, this guy wants me to log in before it serves the data, so let me just do that. Production, sorry. Right. So if you download the, if you hit the download button, you will get the passport data of the accessions documented in this data set. So that means the accessions listed out here. Now, obviously, you can then further filter the accessions, and you can access the details of the different descriptors used in, I should log out. Different descriptors used in this data set. This one is not letting me out. Right. So with that, how do you get to the characterization and trade data sets in Genesys? Either through the Explore characterization evaluation data, which will list all the currently published data sets. There are a number of data sets available in Genesys using the familiar filtering function. You can focus on, let's say, Cassava, and take it from there. So you have different types of data sets available. Also including in Spanish, it just depends on who the data provider to Genesys is. Right, we've reached the 1 hour limit. I'm very sorry for the little drop in the connectivity on my side. So I will have a quick look at the questions. But before I do that, just a second. What I really wanted to do is actually now mention some of the constraints and benefits of the approach taken by Genesys. So as you've noticed, Genesys lets gene banks publish data sets, but it does not make the data set contents directly searchable. Now that's kind of a constraint, but also a bit of a benefit. Now we see really, oh, I apologize. We see really high variability of descriptors, so the definitions, across different data sets, including the same gene bank, within the same gene bank. So that makes it very difficult to build a searchable trait database. Now, this high variability of descriptors across data sets is also one of the strengths of this approach, because each data set may provide the latest, the newest, the fanciest definitions of how those traits were observed. So it's not limiting the gene bank in what trait observations they want to publish, as long as they can document what observations they've made and how they have recorded them. I mentioned we have a lot of sparse data sets, so gaps in data coverage, that happens. And trait data, if you have a huge gene bank with many 10,000 of accessions, it is quite likely that trait data is not available for all the accessions of the, let's say, of a specific crop collection, right? So then making things searchable by trait obviously is going to exclude the material that you have not yet evaluated or characterized or didn't make the data accessible. So it is kind of a risk. So these are the two, let's say, main constraints. The benefits really are that Genesys allows gene banks to publish the trait data sets as they have them. This is one of those really quick, not quick, it's a really convenient way to get data out there as quickly as possible with not requiring too much massaging of data into some standard format. I mean, nobody likes to mess with the data they've prepared. So the best thing to do is publish it as you have prepared it, as long as it's fully documented. Users can search data sets in Genesys. Obviously, the search works by metadata. Accessions are linked to the data sets where they're described. So users can find the trait data that is in Genesys based on metadata alone. And as described earlier, when you have accessions described in a data set, these are automatically linked with their passport data in Genesys, which is most likely current and up to date, including whether the accession is still alive or not. Right, and the approach allows you to provide the exact descriptor lists used in each data set. You can pick and choose. You can make, when you have a trial and you're looking at 5 traits, you can publish data sets with those 5 traits only, and you don't have to worry about the 30 other descriptors that you did not have the resources to look into. So you can publish smaller data sets, and actually those, because they will be more current, those are probably more interesting to users anyway. So, and I think one of the main benefits is really that researchers get the raw data that they can use in their analysis. Now, searchable trade databases let you do some quick filtering, but if you want, and most researchers want to do that, if you want to do some advanced analysis, you need direct access to the underlying data, so that you can link it up with genomic, climate, and other types of things when you do your things. So the approach we are taking is perhaps not the simplest for let's say the simple use cases when you say I want to have, you know, a red leaf cassava, but it allows the serious researcher to download the data and actually do some proper analysis with it, because the traits are properly described in the descriptors uploaded by the gene bank, and those descriptors link to the data set directly. So if you have further questions or ideas or suggestions, you can always find us at helpdesk@genesispgr.org. We're here to help. Anything that was unclear today, get in touch. We will try to organize further, future webinars to address any of the concerns. Or maybe we even have to, chat one-on-one and iron out any open issues. So with that, thank you very much for joining today. Time is up. I'm sorry for the 10-minute delay, and I really apologize for losing the internet connection. That was not supposed to happen. So thank you very much, and have a good Tuesday. Bye-bye.